Where were we? And right in here. All right, so if I recall correctly, we were somewhere around this slide, and we had added a few things to our lists of hazards and things to disconnect. We had put making sure the aircraft was secure, even if it's inside the hangar, because somebody might open the door. We added to our list that you're going to need to ground the aircraft electricity to prevent static electricity discharge. We've already talked about item number 2 there, about doors. That originally, I think, about if you open the doors, it blows, so you need to make sure that there are struts or pieces of metal in the engine compartment or the APU compartment. Connect them too. And let's see, we've already talked about external power and the fact that somebody might have to have external power on while you're doing it. Does anybody remember what do you need to do to make sure that electrical power doesn't get sent to the engine or the APU? Pull the circuit breakers and, well, if somebody has to, I don't think you're going to disconnect the battery, because somebody else might need to operate other systems in the aircraft. Remember, let's just say you're working on a jet, and it's in the hangar, and just swap out the APU or the engine is working. Yeah, zip tie and label the circuit breaker. So it's not that it's impossible for somebody to get out a pair of wire cutters and clip and push the circuit breakers in. It dramatically reduces the likelihood that they're going to do that. And yes, if nobody else is working on the aircraft, I'm going to turn off the electrical as well as pull the circuit breakers and zip tie them and label. I'm not going to say write down, removing the mount access plates. That's a minor detail. Obviously, you're not going to be able to disconnect anything if you can't find the access plates. And of course, here's a nice picture out of the textbook, electrical connections and thermocouple leads. We already talked about the fact that thermocouple leads are generally look different and are different from just generic wires. We've already talked about disconnecting pneumatic ducts. So in case I didn't mention it, so can anybody tell me what's the definition of pneumatic power? What moved by air? Okay, well that's actually what's occurring. Can you define pneumatic power? Let's try it this way. Frederick, can you say what's the difference between pneumatic power and electrical power? Yeah, hang on a second. So you're saying that electricity doesn't have pressurized air? No, you're not saying electricity doesn't have pressure? I would have said electricity doesn't have pressurized air. Be more generic, back up a couple of steps. Just basically, what's the difference between let me ask you this, put it this way. What's the same between electrical power and pneumatic power? It's a very basic question. I'm not looking for big details. That's okay. You have been listening to me ask questions all the semester, so you're not used to it. There's physical movement of air, that's true. Right, with electrical power, electrons are moving, but it's hard for us to say that that's very physical because we can't see it. Okay, so would you say that, so that's very good. So would you say that they're both of these power systems, pneumatic power systems and electrical power systems, do they both move energy from one place to another? Okay. Can both, at the end place where the power shows up, can something get done there? Okay. All right. So you could say that the difference, if we talked about what's the same between a pneumatic power system and an electrical power system, even a hydraulic power system, they all have something in common, is that they're taking energy from one place and they're moving it to somewhere else on the aircraft. Whether it's electrons going through wires or whether it's compressed air going through a pneumatic ducting or whether it's hydraulic fluid that's pressurized moving through hydraulic lines, all of these systems transfer power from one place on the aircraft to another. And generally speaking, it's from the place where you generate this electricity, a hydraulic pump, a jet engine that you take bleed air off of into the pneumatic system, or a generator, and then you run it through a line or a wire, and then you make something move, or you make something get hotter, you make something get colder. You do something with that energy. Has anybody ever heard of that thing called the law of conservation of energy? The law of conservation of energy. John, you were shaking your head down. Pardon me? It's a law of thermodynamics. Can you describe approximately what is the law of conservation of energy? Okay. Go ahead. Well, sorry, you already had a turn. Good. Anybody want to give it, help out, John? Who hasn't answered yet? I know it's tough. How many people in here have taken physics classes? I took physics in when did I take it? The 1976-1977 school year. Oh, wait, and then I got to airplane mechanics school. I went to airplane mechanics school here, 78 to 80. So I was an applied physics. A day or two ago, I talked about the fact that you're all materials engineers. I decided you weren't material scientists, because scientists are trying to figure out something new. You're not trying to find out something new. You're trying to do what engineers do. You take what's already known and then figure out how to make this work without breaking. So you're a materials engineer because you have to take into account, the property of aluminum and steel and all that sort of stuff. So you're also, unfortunately, or fortunately, depending on your perspective, you're becoming an applied physicist. You have to understand physics. And it's not that we're going to do lots of math to be able to figure out how strong this thing is, because an engineer already did that. But we're going to think about it. Well, if I shave off a little bit of this metal, will it still be strong enough to do what it needs to do? Or you're an applied physicist in sheet metal because you're thinking about, I need to put enough rivets in here so we'll hold together as strong as, when I'm done with this repair, as strong as the original piece of metal was in the first place. You're an applied physicist. Does anybody think that's cool? Applied physicist? Of course, the only people that raise their hand are the people that took physics classes. All right. So, somebody that hasn't answered yet. You're on the right track. Energy has to someplace to go. I'll give anybody else one last chance, and then I want to tell you. Okay, Elizabeth, go ahead. Even though you've answered once already. Energy cannot be created or destroyed. It can only be transferred into some other form of energy. Like electrical power, we can warm up the wire, so some of the energy and electricity was taken up and used up by the wire, and the wire got warmer. So we went from power into heat energy. We get to an electric motor, we can convert that energy into rotating motion. Electricity and run it into a light bulb, we get heat and we get light off of it. If we run it into an LED light, most of that energy is light instead of heat. Regular incandescent light bulbs is the other way around. Old school light bulbs produce more energy in heat than they produce energy in light, which is why LEDs don't use as much electricity for the same amount of light. Let's see, how about gasoline or jet? Let's talk about jet fuel. You can put jet fuel in an engine and you burn it. Where does the energy go from this jet fuel? It's chemical energy, but we catch it on fire and it doesn't stay a nice complex carbon. It breaks down into other molecules. Yeah, a lot of it turns into heat, right? Anybody ever stick their hand in the exhaust pipe of a running jet engine? Yeah, good. If you haven't done that, I highly recommend you not do that while the engine is running. Yeah, so we get a lot of kinetic energy. Kinetic just means it's moving. Kinetic energy means it's moving. So we're going to turn a lot of that energy into air that's blowing out the tailpipe, or we could also turn it into energy in air that goes through the ducting inside of the airplane. So I'm actually slowly coming back around to pneumatic power. Pneumatic power is a power system that is based on energy transfer using air as the thing that moves with the energy. Pneumatic power systems use air to transfer power. And generally speaking, this air is made up of two things. It's made up of high pressure and it's made up of high volume. So this is important enough that I'm going to write this down. So pneumatic power. See if I can be concise here, because I don't want you to have to write 17 sentences to get that question right. Pneumatic power uses air to transfer energy. So that's one. And this air has three things. So I'm going to use it has pressure, and it has volume, and in some limited circumstances, it's transferring power because of heat. Can anybody, we'll go try the hard one here first. Can anybody think of a use of pneumatic power where, if you haven't raised your hand yet, where a use of pneumatic power where you need to get some heat somewhere and you're using compressed air to get that heat somewhere? Kittrick. Yeah, that's great. A air system for a leading edge de-ice. Leading edge de-ice is on the front of the wing. You literally pump air off of the compressor of the engine, and it's hot. If you've compressed it 2, 3, 4, 5, 6, 7, 8, 9, 10 stages of compression, it's about 200-300 degrees Fahrenheit, 400 degrees Fahrenheit. It's like the inside of an oven. So that ducting, are we going to make it out? Come on, I know there's some materials engineers out there. Yeah, we probably aren't going to make the duct out of aluminum. We're probably going to make it out of stainless steel. So why would we make this duct? Why would we not have this duct made out of aluminum? Somebody who hasn't answered yet. Say that again, Brian? Yeah, because aluminum will be completely liquid at 1100 degrees Fahrenheit. If we heat it up to 400 or 500 degrees, we're going to change the strength of the aluminum, and it won't be strong anymore. We're going to be heat treating it when we shouldn't be heat treating it. So if we need that to be able to withstand 400, 500, 600 degrees Fahrenheit, the engineer is going to decide, okay, let's not make this out of aluminum, let's make this out of stainless steel. Okay, so now if you understand what I'm talking, who does not understand that aluminum melts at a lower temperature compared to stainless steel? How many people in here have taken a torch and melted aluminum? Okay, obviously not enough of you. So maybe I'll need to do that on one of these days. I'll ask Mr. Parsons. I know we got some scrap aluminum. We need to take a piece of stainless steel and a piece of aluminum and put a couple of propane torches on them and see which one we can melt sooner. Because the aluminum melts way sooner. In fact, if you want to build a forge in your garage and melt aluminum cans, you have to get up to 1100 degrees Fahrenheit. I don't know about stainless steel, but regular steel, it's more than twice as much. 100 degrees Fahrenheit. So it can handle a lot higher temperatures before you change it. All right, so that was a great example, Kittrick. The energy coming off of the engine, we didn't need, it's not so much the volume or the pressure of the air, but we needed the temperature. We needed the heat energy of the air to get transferred out to the front of the wing. Has anybody ever flown an airplane through the sky and had ice stick to it? I have flown an airplane through the sky and had ice stick to it. And I went, ah! No, because it was a little tiny airplane that have de-icing systems on the wings. Well, I was in the middle of the clouds. I could have climbed 3,000 feet, and I'd have still been in the middle of the cloud. I don't think getting 3,000 feet closer to the sun would have done anything. I think that's, what's the sun, 98 million miles away? Something like that. All right. All right. So I'm not going to go into de-icing systems. So when somebody says pneumatic, the first thing you need to be thinking of is this is a power system. It's going to move power from one place on the aircraft to the other, and it's going to use air to move the power. It's not electrical power. It's not. And we can use pneumatic power because we can have this air at a high pressure. We can have a lot of volume. That's a whole bunch of it. That's a large quantity of air, a large amount of air. That's the volume. Or it can have a high temperature. Or it might even be all three of those. In my opinion, and I mean, I guess my opinion counts because who's writing the tests? Yeah, me. So I guess my opinion counts. I think it's very important. If you're going to be a reasonable jet aircraft mechanic, you need to have a pretty good working understanding of pneumatic power systems, because that's really what's operating a jet engine. And I know Mr. Asman has spent the time on the theory of jet engines, but the whole theory of operation of a jet engine is talking about pneumatic power happening inside of the engine. It's just now we're talking about pneumatic power being extracted off of the engine and being used for things. So, you can expect there's certainly a possibility that there will be a test question or two about pneumatic power. But we've already put on our lists pneumatic ducting having to be disconnected, so we're not going to add that to the list. Electrical wiring connections, we talked about engine instruments. We've talked about several other kinds of electrical wiring connections. We talked about control. We talked about electrical power. So we don't have to add to our list more electrical and more engine instruments and more pneumatic ducting. You remember that list of things that you have to disconnect to take an engine out? So what we need to get off of this slide is the definition of pneumatic power and what are the three forms of power that pneumatic power is made up of. It's made up of pressure, volume, and heat. All right, fuel lines. Have we put fuel lines as something that we have to disconnect on our list? I believe we have, so we don't have to write that down. But guess what? I believe we haven't talked about hydraulic lines yet. So just for fun, so you can go to that list. Here, I can go to that list too. Disconnecting. And so we're going to need to be able to connect and disconnect. Hydraulic lines. And I'm going to put an S on there. You got to understand that on a lot of aircraft, there's a hydraulic pump on that engine. In fact, I can think very easily of at least different ways to pull power off an engine and send it to the rest of the aircraft. It's pretty simple. What is aircraft engine? Well, the big ones hanging out on the wings or the fuselage, they generate power to push the airplane around on the ground and hopefully in the air. If it's a jet, hopefully you get to go 500 or 600 miles an hour and you get to go woohoo. Can anybody think who hasn't answered a question yet today? Can you name one of at least three different types of power that comes out of the engine, the main engine? It comes out of that engine compartment and it goes to somewhere else in the aircraft. I know there's like 30 people out there that haven't answered a question today. Say that again? You can get pneumatic power from the engine, yay. And so far, except for one exception, that pneumatic power typically comes off of, anybody that hasn't answered yet, where does that pneumatic power come from off of the engine? Come on, jet engine physicists here. Amir? Yes, it comes off of the compressor. And somebody else who hasn't answered today, what do we call this air that we take off of the compressor? We have a particular name for this kind of air, Brian? Bleed air, because we're really bleeding energy off of the engine. Okay, very good. Okay, so pneumatic power comes out of that engine compartment. Can anybody think of something else that's bolted onto the engine that we take power off, put it into some other form? Anybody that hasn't answered a question, I can start going down this road. You want me to do that, or you want me to give everybody a chance to answer? Who's that? Yeah, Evan. What did you say? Bolt electrical generators onto engines. In fact, I have never heard of a turbine engine that didn't have an electrical generator on it. I take that back. I can think of one. In a CH-47 helicopter, it's a big twin rotor job. Army has a whole bunch of them. The auxiliary power unit, you start of that turbo shaft, spins a hydraulic pump, and it uses hydraulic power. And it actually has a hydraulically powered starter motor on the main engines. So that's the only turbine engine I can think of that doesn't have an electrical generator on the engine. One out of 1,000 different. So how many people in here are likely to go in the U.S. military and work on CH-47? Likely to go in the U.S. military? Okay, great. But however, there are a few companies in the world that operate civilian versions of the CH-47. Columbia and probably Evergreen operate. I know Columbia operates CH-47s because I have a former employee that's a co-pilot in the Middle East flying CH-47s. All right, so if you haven't answered a question so far today, then you get to answer this one. What is the third, can you name a third power source coming off of an aircraft engine? We've talked about bleeding air off of it and having pneumatic generators generating electrical power. Say that again? Hydraulic power, very good. Yes, you can bolt a hydraulic pump to the engine, and it can provide hydraulic power. So how many engines bolted onto underneath the wings or on the side of an aircraft, the engines that move the aircraft, the engines that are on all the time, how many of those big aircraft have hydraulic systems and need hydraulic power? Anybody? Yeah, I heard an all. I'd say, yeah, 99.9% of them have hydraulic systems on them. Can anybody name an exception to that? I'll give you a hint. It's big, and it's made out of carbon fiber. What? The 787. Yeah, the 787 is a very unusual aircraft. I'm not going to go into too much detail, but almost all of the systems on it run off of electricity. And in fact, the starter motors are electric. The APU that fires up has a big giant generator on it to provide electric power to use start on the jet engine, which is electric. Oh. The air conditioning? No, which is a great answer. They actually use electrically powered air pumps, electrically powered air compressors to keep the airplane pressurized. Yes, very good, Elizabeth. The heat for the inlet of the engine, the intake heat, is the only thing that takes bleed air off of the engine. There's no pneumatic ducting that leaves the engine compartment. Everything, I'm trying to think. I'd have to look up. I'm going to look it up at break and see how much hydraulic systems are on the aircraft, or is it electrically powered? All right. So the good news is, though, the vast majority of airplanes out there, 99% of them, have hydraulic pumps, and therefore, if it's the main engine, you're going to be connecting and disconnecting hydraulic fluid. Now that brings up a really good point. Some of you, let's see. I want to talk to the first semester students who haven't heard the word hydraulics very often, unless you have a lowrider and a bunch of batteries in the trunk, and you got those levers on some, and you move the levers and the car bounces up and down because you get the springs going and the hydraulic actuators. Has anybody ever seen one of those cars? 2 or 3 people have seen those cars. All right, those are electrically powered hydraulic pumps, and the hydraulic pumps make pistons go up and down and push the car up and down. So that's hydraulic. It's a lot like a pneumatic system, except it uses a fluid instead of a gas, a fluid instead of a vapor, a hydraulic fluid instead of air. Now, in little tiny airplanes, like the ones we have out here, the hydraulic fluid is made out of petroleum products. It's not as bad for you as gasoline. I'm not suggesting you drink this kind of hydraulic fluid. It's called 5606, and they put a dye in it so that you can see the leaks easily. But if you get it on your skin and you rub it around, and you shave with it, it's not so terrible. It's not really any worse than engine oil. It's not that it's pretty. It's not, I don't know, maybe it does feel good, but that's another discussion, see me after class. But it's not terribly poisonous. And that's the kind of hydraulic fluid you find in little airplanes. The problem with 5606 is that it's not lightweight. It's not really, really heavy, but it's not lightweight. And in a little tiny airplane, you only got 2, 3, 4, 5, maybe 5 or 10 pounds of it on the airplane. Usually make the landing gear go up and down. It's not big of a deal to try to use a fluid that weighs less. But when you start talking big business jets and big airliners, even small airliners, instead of having 5 or 10 pounds of hydraulic fluid, they have hundreds and hundreds of pounds of hydraulic fluid because lots of things on the aircraft run. Let's think hundreds of pounds, tens and tens and tens of gallons of hydraulic fluid. If hydraulic fluid gallon, but we can have this special kind of hydraulic fluid that only weighs 4 pounds a gallon times 100 pounds. Weight. So let's say you could say, yes, or 50 gallons more, or you can have the same volume and save 200 pounds. 200 pounds, that's an extra passenger every time you go flying. Think of how much money that airline could make across a 20-year period that it owns an airplane. For 20 years, they can put one more person on that airplane for every single flight. Is the airline going to say, yes, I want that? Of course they're going to say that because they want to make money. The problem is that this kind of hydraulic fluid, it's called Skydrol, is that it's bad for you. You need to not shave with it. You need to not get it on your skin. So I'm going to write down the word Skydrol. Actually, what I'm going to do is, do we have some hazards? Hazards. Here we are. So some of the hazards, oops. I'm actually going to use the word Skydrol instead of hydraulic, because regular hydraulic fluid is not so bad. You know what? I don't like the word spills. Skydrol. Let's see. Yeah, let's do it like this. This will make a really good impression. Skydrol poisoning, because that's really what it is. That's really what it is. I'm not exaggerating here. Skydrol is really bad for you. You got to pretend it's worse than gasoline, because gasoline gets on you, a little bit of lead goes in you, a little bit of hydrocarbons, carbohydrates, a few hydrocarbons get in you. If it's gasoline, it evaporates. Most of it doesn't soak in your skin. Jet fuel's a little bit worse. If you leave jet fuel on you, have y'all talked about the hazards of jet fuel? It irritates like a mother. Yeah, so your mother's very irritating? Okay, I know how you feel. I'm living with my mother right now, but that's a whole other discussion. Is it made with, why is Skydrol so poisonous? Is it made with arsenic? I don't believe it's made with arsenic. The why is a really good question. I appreciate that answer very, very much. All I know is engineers were looking for years and years trying to figure out a way, how can we have something that is a fluid and it lubricates, just like regular old school 5606 red hydraulic fluid does, but it weighs a lot less, so it's worth doing, and the only thing they could come up with, and it's compressible. That is, if you try to squish the fluid, it doesn't change its volume. So that's very important with hydraulic fluid. You can't squish it. Or you could say it's not squishable. In any case, the only thing anybody could come up with was chemicals that are not good for humans. Is somebody trying to come up with a better version? I don't know. You're asking a good question. Or you can have hazardous things in California. You just have to pay more attention. You just can't kill people as often. Or you have to warn them. You have to warn them. You have to pay more out of pocket. Okay, so we've added to our hazards, and let's see, we've added to our, what was this list? Things we have to disconnect because of turbine engines. So I'm going to hit keep, and I know y'all have had a bad day, so we're going to call it quits for today. I'd like you to be in lab at 30 minutes after.